Next section, we're going to deal with exponential functions and graphs. The reason why these two exponentials and logarithms go together, which is the reason why we learn inverse functions, because they are just that. Those are inverses of each other. We're first going to look at what is an exponential function. The function f of x equals a to the power x, where x is a real number and a is positive and not equal to 1. But up until now, our functions were always x to the power of some number, where the x was the base and the exponent was anything. Now with exponential functions, our variable is the exponent. Let's look at a graph. The most common value we use is 2. You notice it says it cannot be negative. The base cannot be negative nor 1. If it was 1, then it'd be a horizontal line. It can't be 0 because 0 to any power is 0, so that has to be a horizontal line. It can't be negative because if it was negative, if the exponent was negative, or if the base was negative, and the exponent is even, then the answer would be positive. If it's odd, it'll be negative, so it'll always oscillate. So that's why we have to have the base has to be positive and not equal to 1. So what this says, we have to look at 3 parts here. X being negative, x equals 0, and x being positive. So 2 to the power negative 2. That's the same as 1 over 2 squared, because when you have a negative exponent, you change the position. So that becomes 1 over 4. So if my x's are all negative, all it means is you get very, very small. If x is 0, it equals 1. So that's my y-intercept. And if x is positive, it keeps on going bigger, bigger, and bigger. So what the graph of an exponential function looks like is this. It's an increasing function. The horizontal asymptote is the x-axis. The y-intercept is 1. And it goes on to infinity. It's continuous. Well, let's look at all these conditions, the properties of all these. For this first one, we're going to look at n being, or a being greater than 1. It's an increasing function. Continuous. Passes the one-to-one test. Domain is negative infinity, positive infinity. The range is greater than 0, can never equal 0. No x-intercepts. The y-intercept is at 1. So it's at 0, 1. That's for when a is greater than 1. Remember, the conditions we had is a had to be positive and it could not equal to 1. So we have to look at what happens when a is between 0 and 1 and what happens if it's greater than 1. Well, that's what happens when it's greater than 1. If it's greater than 1, then it's an increasing function. Now, if a is between 0 and 1, let's say our function looks like this. 1/2 to the power x, or 1 over 2x. Now, what this graph looks like, as x gets bigger, as x gets more bigger, this whole number becomes smaller. When x becomes bigger negative, then it goes up. So this graph looks like this. Decreasing function. Because 1 over 2 to the power negative 3 is 2 to the power 3, which is 8. 1 over 2 to the power negative 4 is 2 to the power 4, and that's 16. So the bigger the negative, the bigger the answer becomes, the higher it goes. It's continuous. It's 1-to-1. The domain is all real numbers. The range is greater than 0. No x-intercepts. The y-intercept is equal to 1, so it's at 0, 1. And there you have it, same thing. Again, we have to remember our rules of exponents. Whenever you have a rational, when the base is rational, as long as it has to be a proper fraction. If it's improper fraction, then it's greater than 1. This one, it has to be between 0 and 1. If it's between 0 and 1, then it's a decreasing function. Let's look at transformations. Actually, yeah, so that's the reason I'm taping this so we can move on, because I want to try to finish before next week's over. We just have 5 more sections. Okay, using our transformations. What do we notice about this one? Well, Since our function is not affected until x is affected, this is a horizontal shift. So x minus 2 set equals 0. So it moves to the right 2 spaces. So my origin shifts from here to there. So my graph now looks like this. My vertical intercept, the y-intercept is still at 1, but it's shifted over, so it's at 2, 1. B f of x equals 2x minus 4. There's no horizontal shift. No, but there's a vertical shift. So the whole graph, remember, it used to cross at 1. But now I have to shift my origin down 4 spaces. So there's my new origin. My y-intercept is still 1 up. And there's my graph. Just a vertical shift. This one has a couple of shifts. First off, the base is between 0 and 1, so it's a decreasing function. The sign of the value, it's outside the function. So since it's negative 0.5, it flips across the x-axis. Doesn't change x. X's are still where they are. It just changed the answer. And there's a vertical shift of 5 up. Two, 4, 5. So my origin shifted from here to here. So 1 below the origin is my intercept. So there's my intercept. That's what the graph looks like. Remember, go back to your chapter notes for transformations. If we were going to flip across the y-axis, then x would have been shifted. That's a shift across the x-axis. That's a rotation around there. I'm on the y-axis. But since it was out in front, it's a shift across the x-axis. Right. Okay, that's just a review of transformations. Here's an application problem. Compound interest. There are 2 types of interests, compound or simple interest, that banks usually use. Simple interest is It's a one-time fee assessed to you how much money you're borrowing, and you pay back your amount you borrowed plus that one-time interest. Compound interest is the one that keeps on hitting you, however much money you have outstanding, it keeps on hitting it over and over and over until you pay it back. The amount of money that you still owe, that's called an annuity. That's how much money you still owe. P is called the principal. That's how much money you borrow. R is the rate in decimals. That's the interest rate that you're paying. N is the number of payments. If you're paying by year, by month. If you pay quarterly, it's 4 times. If it's paid annually, it's 1 time. If it's paid weekly, it's 52 times. Daily, it's 365. And then your exponent is n times t. Number of times compounded. Okay, suppose you invested $100,000 at 6.5% interest, compounded semi-annually. How much would your investment grow in T years? So the principal is $100,000. That's how much I borrowed or put in the bank. The rate was 6.5%, which becomes 0.065 we divide by 100. So that means move the decimal 2 to the left. 0.65. N is semi-annually, so N is 2, you pay twice a year. So it's 2 times T. There's the formula that how much money you would have after T years. What if T equals 4 years? So it's 100,000 times 1 plus 0.065 over 2, 2 times 4. And whatever that number is, that would be it. And that's all it's asking you to do there. You would enter this stuff. You'd first do 2 times 4 is 8. Work inside the parentheses to the power 8 times 100,000. And that's how much your note is worth now. Euler's number, E, is a very important number. It's a constant, 2.7182818, blah, blah, blah. It's a natural constant. It's one of the only numbers on your calculator besides pi. E is one of them that's on there. And what you're going to see, on your keypad, you're going to see e to the power x. What you do is you'll press that button, and then it'll ask you for entry. So you can put something like that and enter, or you can put -2 or e to the 0, which is 1. You can put whatever you want to in there, and it's just going to give you that answer. All right, that's it for that one. No, we're just now opening the door for exponentials, because the opposite of this are logarithmic or logs. Those are the inverses of exponentials. Because think about it. How would you solve for x? We can't solve for x because it's up top there. Logarithms bring it down. Yeah. And once you see it, it's super. It sounds, a lot of people think it sounds tough, but once you see it, it's Mickey Mouse easy. That's why I'm not really worried about this chapter. It goes really smooth. Here, take pictures.